Good evening, everyone, and welcome to Observatory Nights at the Harvard-Smithsonian Center for Astrophysics. Tonight's topic of consideration is planets. Now, the term planet came from a Greek word for wanderer, and that's because for thousands of years, all we knew about planets is that they were these bright points of light that moved across the sky against the background of fixed stars. It wasn't until the telescope came along 400 years ago that we learned that planets are actually worlds, and like Earth, they circle the sun. So, of course, then the natural question was, well, where did these planets come from? How did they form? And scientists came up with many different hypotheses. Some scientists suggested that the early sun may have been spinning very quickly, and maybe it spun so fast that it actually flung chunks of itself off and spewed them out into the solar system. Now, some other people thought that, well, maybe it was a fluke event, and we started with the sun, and then a rogue star came along and passed really close to it, and the tidal forces ripped off this material and sent it out. Now, of course, now we know that the sun and the planets formed together from gravitational collapse of a giant cloud of material inside of a molecular cloud. But that's definitely not the whole story. There are still many details that we're working out and many questions that astronomers want to answer. And that's particularly true now that we have discovered exoplanets. And our theories have to explain not only our own solar system, but the incredible variety of other planetary systems that we are finding out there in our galaxy. Now, tonight's speaker, Anjali Tripathi, is an astrophysicist and PhD candidate at Harvard University, whose research focuses on the formation and evolution of planets throughout the universe. Now, she tackles these big questions with computer simulations and also statistical analysis. And she is currently working on using data from the new ALMA array of radio telescopes to play a sort of a cosmic Where's Waldo and try to find places where planets are forming and also to study their birth environments. Anjali has an amazingly diverse background. She has worked on the mission operations team for the Mars rovers Spirit and Opportunity. And she also played a role in the Mars Reconnaissance Orbiter that we showed a video of before our live webcast began. She was at MIT. She was a member of their solar vehicle team. And she's the only person that I know personally who has driven a solar car. So I think that's pretty cool. Her work in engineering, particle physics, and astronomy has been recognized with a number of prestigious awards. And she is also a skilled communicator and an enthusiastic astronomy outreach ambassador. I am very pleased to hand the evening over to Anjali Tripathi.
So tonight's talk, you might think, is a very natural question. Where do planets come from? Here at Harvard, you see a lot of talks talking about all kinds of exciting worlds, but we seldom touch on this question, where do planets come from? And as you'll find out throughout the evening, this is a question we've been thinking about for centuries, as Christine mentioned, but it's only recently that we're actually able to know how planets form and where they come from. So in that vein, let's look at the night sky. So what you can see here is a WIN, an observatory from the National Optical Observatory. And that X that you see in this beautiful night sky image is the field of view where the Kepler spacecraft was looking. So the Kepler spacecraft is a telescope in space that's been used to discover planets. So in the course of Kepler's main mission, it discovered over 1,000 planets, and that's just in that little field of view in the sky. So all of those colored dots you see are planets. And of course, it only looked for a few years. So as a result of this and other planets that we've found, we now believe, astronomers as a community, that planets are common, right? When you look at stars, every star you see, or almost every star, has a planet, or maybe even a few. That's just incredible, right? I mean, we could say an entire talk about that, because I still remember when I was young, there were 9 planets, then there were 8, and then they kept going. And when I was in college and doing my research, we were still only in the realm of a few hundred. But now we're almost at 2,000, and that's just incredible. And as we're finding planets, what we're finding is not like our own. So just to be clear, most of these are artist impressions of the planets we're looking at, because we can't see the planets directly. But there are a couple planets that you might be able to find. I know that Earth and Mars are in here. Mars is hiding just over here, if those of you can see above. And the Earth is up there, sort of to the right of that big brown fellow. But what this plot is meant to show you is that there's just this incredible diversity of planets, because this is actually arranged with things that are rockier at the top and things that are hotter are to the right. That's why the Earth is to the right of Mars. And so as we're finding planets, we're finding that they're all different. So if you thought the question of planet formation was hard in the 18th century when you had just a few planets to worry about, now try explaining all of these and think, oh no, where do planets come from? Right? And so, like I said, there are many theories about what's going on, but I am a scientist. I really want to focus not on just what we think, but how do we actually know this? So the way we're going to attack the question of where do planets come from is by how do we know it? So I'm only going to present results that are observationally motivated. You might say, but there are so many other things to talk about with planet formation. And that's true. We have to get from dust to life in 40 minutes. That's not going to happen, right? So we're just going to talk about what we can motivate observationally. And the 3 lines of evidence we're going to use for this are shown with these 3 images here. So the first we're going to start with is within our own solar system. So when you think of the solar system, you might think of the planets, right? Like what else would you think about in the solar system? Well, the word solar suggests that you should think about the sun. So the planets in our solar system are orbiting around the sun, right? They're gravitationally bound. They go in these pretty circles around the sun. But you often see pictures that look like this. Oh, and for those of you who might have noticed, we've got a straggler tacked on at the end. So I've included New Horizons' view of Pluto with its heart shape on it. And the reason is because Pluto is a dwarf planet, and for the purposes of this talk, he's a planet. So all of you who are stressed about Pluto not being there, he's here tonight. Okay? All right. So now that we've got that out of the way, Pluto and all of his buddies orbit the sun. And so let's look at what that looks like. So I'm going to show you a movie of how the planets are moving around the solar system. And so we're going to start here on Earth. And that red circle that you see is the orbit of the moon around the Earth. And we're going to back out so we can see what this orbit looks like. So let's start. So as we're moving away, of course, you see the sun, which we're going around. And you can see interior to us are Mercury, Venus, there's Earth, and there's Mars. And you see that we're all going in the same direction, right? These bright points show you where it is at the time this movie was made. Now you have the giant planets, Jupiter, Saturn, Uranus, and Neptune. And now let's look at this. So this is actually accurate. So this is created by the American Museum of Natural History. The locations of all of the stars are accurate, like you would see in the night sky. The positions of the planets, their orbits, all of this is accurate. So you might notice something, though. It's flat, like a pancake, right? You might have expected maybe planets should go whizzing around, kind of like when we draw a picture of an atom and we say the electrons are moving around in a planetary model. But the planets in our solar system don't even look like that. They're all in a plane. So what is this telling us? Well, this is telling us something about planet formation, actually. And that is the fact that they're all moving in the same direction and in a plane is that they might be coming from a protoplanetary disk. And this isn't a new idea. This was thought up by Laplace and Kant in the 18th century. So just from looking at our own solar system. So you might say, well, what is a protoplanetary disk? What does that look like? So a good way to think about a protoplanetary disk is by looking at Saturn. So I'm very biased. As Christine mentioned, I spent some time at JPL, and the Cassini mission was just doing all kinds of awesome things while I was there. And so it took this picture. And before we talk about how this is like a protoplanetary disk, I just want to tell you that this picture is the ultimate selfie. Okay? So is there anybody in the audience who is younger than 3? I don't hear any crying, so I'm going to go with no. Okay, so you are all in this picture. Do you see yourself? No, okay. Well, the reason it's the ultimate selfie is, first of all, because that little dot that you see here is the Earth. And you can see some other planets shown there. But this is actually the first time that a spacecraft took a picture of Earth, and the people on Earth were notified in advance. So there was actually a whole campaign run by NASA called Wave at Cassini. And so this picture is called The Day the Earth Smiled. And you can go online and check it out and see everyone's selfies that they've mosaicked onto this image. Okay, right. But less selfies, more science. So the reason I think that you should think of Saturn like a protoplanetary disk is that it's got these rings that are very flat going around the planet. So instead of the planet Saturn, you can think of that as being like the star at the center of a protoplanetary disk, right? So we're all orbiting the sun, and so the disk material is going around that star. And then you can see that I've marked all of these objects here, right? You can see that there's the moon Tethys down here, which you can see. You can see Enceladus up here, which streams jets of icy material, which Cassini has also found. We've had all these amazing discoveries, but you notice that there are planets that are not just far away. There are planets actually within the rings, as you can see with Prometheus, and we'll talk more about him a little later on. And so this is actually a really nice analogy for how protoplanetary disks work, because you have a star, you've got a disk of material around it, and you've got bodies within it. Whether they're moons or planets is different, but it drives home the point that planets are forming around stars in protoplanetary disks. So what do I mean by the protoplanetary disk is around the star? Like, how does this happen? So I want to show you a movie of how the gas cloud that's actually used to form the star then further collapses right into a disk out of which the planets can form. So you'll see something collapsing. It'll start round, and then it'll keep spinning, kind of like pizza dough, and it'll flatten into a disk. And out of that flattened disk, a star is going to grow. 95% or so of the material in this cloud and disk is going to become the star. The planets will just be made out of some of the scraps. Okay, so what are we looking at? So we're first going to dive into this cloud, right? A star is bright, so we're going to sort of go there, and we're going to see this cloud of gas. So like I said, you can see it turning, and as it turns faster, and you can see some time has elapsed, it's become a disk. So the star is forming, and this isn't showing you about planet formation, this is just to give you an idea of the disk itself. But you can see that over time, the disk starts to thin out, partly because the planets are removing some of the material, and partly because the sun also is hot and it's blowing away material. So you'll see it'll sort of clear out towards the center too. And so this is going to happen over time such that what we're left with is not a disk that you can see, but just the planet going around the star. So we'll talk more about this in a minute, but you might be saying, well, what can we see? What do we know? And the question that you might then think is, well, what part of it could we see? And the answer is basically none of it, because it takes about 10 million years to form a planet, give or take 100 million years, depending on the kind of planet you decide you want to make. And I think it's a fun chart to think about how long it takes to make various things, right? So it takes 3 weeks to get a rat, which might be a cause of concern for some of you right now. Never mind. It takes 9 months for a human. And it takes a couple years to get an elephant. So the bigger the thing, generally the longer it takes. Of course, this isn't a hard and fast rule. Some bigger things take less time, like a whale is less time than an elephant. But a planet is a lot bigger. And if we were making a scale bar like that, this scale bar would need to go on about 1 million times further. So it's not going to fit in this room. But you might think that that's a really long time. But actually, that's a really short time in the lifetime of a star, right? Stars live for billions of years. So a few 10 million years here and there is not a lot. So if this takes such a long time and we don't live for 10 million years, how can we say anything about planet formation? Well, the answer is coming to us from outer space and comes right to our doorstep. So, meteorites are actually a really useful tool for studying planet formation. And the reason is that they're actually left over from that protoplanetary disk. So you can think about this as a diagram of the early solar system. So you can see there's material in a disk, and you've got a proto-Earth, a proto-Mars, a proto-Jupiter. They're still forming. The sun is young, but it's mostly formed. But what you see here is the asteroid belt. Do we still have an asteroid belt today? Can anyone tell me? Yes, all right. And you know it's a belt, right? It's not a cloud, thus going with that whole idea of things are in a disk. So meteorites come to us from asteroids, and Jose talked about this in his talk a couple months ago. But of course, asteroids sometimes come close to Earth. Sometimes we have meteorites coming to us, and that gives us samples with which we can actually study that early disk. So, courtesy of the Harvard Museum of Natural History, we've got some samples tonight that you can look at. So this is a particularly shiny one. For those of you who are not in the auditorium right now, you should know that the images on the screen are actually what we have here with us in the room. And since it is cloudy out tonight, that was why I brought these, one reason. So everyone here and in the overflow rooms can come up and look at them at the end. But the thing is, right, so everyone's like, oh, can I go see that right now? But let's see, let's focus on planet formation. Okay, right. So meteorites are important for planet formation because if we date them using radioactive isotopes, we actually find that they're older than the Earth. It's not that they're as old as the Earth. They are older than the Earth. And not only that, so it tells us that this is coming from that protoplanetary disk, and we can study planet formation by looking at them. But we can do more than just look at them and admire them. We can tell something about the composition of what that disk was like. So we're getting stuff from space delivered to our doorstep. And so in the different classifications of meteorites, which I've shown you here, which are these stony iron, and iron meteorites, you can tell something about how the processes happened, right? So an iron meteorite, so this is a solid block of iron. For those of you wondering, the sample shown there, this sample weighs about 15 pounds. And you can see that it's real. It's not something we made in the lab because this crisscross pattern of crystallization takes millions of years to form. We cannot actually synthesize that in the laboratory. So anyhow, you need something very hot to melt and then slowly cool to get something with iron. In the stony iron, you've got these peridot crystals, right? These olivine crystals. So if anyone's birthday is in August, that's your birthstone, more or less, embedded in that metal matrix. And so that comes from another part of a forming planet. And the stony meteorites are what I think are the most interesting. You might say they aren't the most pretty, but they're actually the most helpful to us scientifically. And that's because you can see all of these little circular features. I've highlighted a few. There are many more out there. And the reason is that these features are called chondrules. A chondrule is a droplet of material from the protoplanetary disks that has been preserved. So these droplets in space that somehow managed to get encapsulated up and managed to survive until the present. So by studying chondrules, we can actually study what the solar system was actually made out of. So we find chondrules that have water, that have carbon. There's a lot going on in there. And so I think these are some of the most exciting things that you'll see. And our sample, which is shown up there, when you come up and look at it, you should definitely look at the chondrules. So by looking at what the meteorites are made out of, we can see what the planets are actually made of. And we can get an idea of the chemical composition. And so overall, we feel that the planets are made generally of dust, gas, and ice. So when I first heard about space dust some years ago, I have to say I laughed, right? Because dust is that thing in your house. We don't talk about it seriously. But for planet formation, dust is serious stuff. So on the left is a picture of some dust that was collected by an airplane at high altitude. And you can see it looks kind of fluffy, right? So it's about the size of 2 red blood cells. It's a few microns in size. And if you want another way to think about it, you can think about it as the same size of particle as in smoke. So that's why I have a picture of smoke on the right. So a planet forms out of dust and gas and ice. But, there's a lot of mysteries how you go from something that's a micron in size, 10 to the minus 6 meters, up to a planet, right? In between, we have rocks and then planetesimals that are various sizes, right? You've got things that are a few inches here up to kilometers, and then eventually thousands. So what's going on here? Well, we don't have a video camera to capture the whole process, but our best guess is that a lot of this has to do with growing planetesimals. So I'm going to show you a movie now of zooming into a protoplanetary disk and to see what that growth looks like. And again, this is based on our best guess of what happens. So you see the star at the center, you see this gassy material, and now we're going to zoom in and we can see what's inside. All right, so you see that there's some gas, which looks kind of like a wind, and there's lots of different particles whizzing around. You see some green things, which are sort of more like the olivine, and you have all these dust particles now. So you'll notice they do a couple different things. Sometimes they stick together, sometimes they bounce off of each other, and sometimes, especially when they're bigger, the two of them collide and break. So if you want to grow a planet, you really need these things to stick together. And so what people do actually are experiments in drop towers and even on the space station with particles of dust to see how do they stick together, and try and understand how planet formation works. Because again, this isn't something that we can go out and see in person, especially at such small scales. So since I'm focusing on how do we know what planet formation is like, I'm not going to go more into the details of this now because the universe doesn't provide us that information. But one thing it does tell us is that planets, though, aren't just big balls of rock, right? I mean, we call the 4 planets, Mercury, Venus, Earth, and Mars, the rocky or terrestrial worlds because there's a surface where a rover can land on, right? You can't put a rover on Jupiter, Saturn, or Uranus, or Neptune, right? There's nothing to land on. So you can tell, though, that you need not just dust, but you need other components. So when you add ice to the dust, it actually makes it stickier and easier to grow something larger. But of course, you need an atmosphere in these planets. So I think of adding an atmosphere to a planet like making cotton candy. Because when you have cotton candy, you start with a core, like a little cone or stick, and you whiz it around, and the sticky sugar sticks to it. And that's just like adding gas to an atmosphere. So the bigger your cotton candy is, the larger it will grow to be, right? And as this artist in China can do, he can make you flower-shaped cotton candy. But the thing is that just because you start with a core doesn't mean that you're necessarily going to end up with the same thing, right? Maybe you'll have something round, with one layer, maybe lots of layers. It's not a hard and fast process, but we do know that the bigger you are, the more gas you get, and getting an atmosphere is just a very natural part of planet formation. So you're going to say, well, that's nice, but I still really want to know, where do planets come from? And tell me more. So sort of the final frontier, and where we are focusing a lot of energy on studying planet formation, comes from pictures like these. And that's by doing something like this. We actually directly observe these protoplanetary disks that I mentioned. Because within our own solar system, we can get pieces of the protoplanetary disk back on Earth and we can look at our orbits. But we actually want to look at a large sample to explain that whole diversity of planets that we're seeing now. So I mentioned that protoplanetary disks involve planets going around a star, or forming near a star. So if you're going to look for a protoplanetary disk, the place you want to look is around where a star is forming, because the protoplanetary disk happens while the star is forming. So here's a beautiful infrared image from IRAS, this infrared satellite, showing some of the nearby star-forming regions. So up at the top and sort of down on the side here, we've got the Taurus-Auriga complex. And further down where I'm standing, we've got Orion. It's hard to see the constellation here, so I'll show that to you in just a second. But you can see, right, the stars glowing brightly. And it's sort of easy to see where these star-forming regions are to get a sense. But stars shine, and protoplanetary disks and planets don't. That's why it took us so long to discover them. So how are you going to see them? Well, in the 1990s, the Hubble Space Telescope was looking at Orion, and it made a really interesting discovery. So this movie is going to show you that. So as you can see there, you can see Orion's belt, and you can see, some of his legs. So we're going to zoom in to sort of below the belt, shall we say. And we're going to go into what's called the Orion Nebula. So as we do this, right, you see stars here, but you're going to see lots of really colorful gas and some dark areas. Those dark regions are where you have gas and dust and all the things to form stars and planets. Okay, so you can see the star forming region, and you're going to soon see a planet forming. Okay, so if you all saw the protoplanetary disk, that's great, but now you've missed it. All right, fine, I hear some whimpers. We'll go and look at it, okay? So it's off further away from where the star is forming, and it's this dark spot there. Like I said, those clouds of gas and dust were dark, and so this is kind of like the shadow of a protoplanetary disk because it's absorbing light, right? So it's not shining. And we call this a proplid. Proplid is short for protoplanetary disk, and like I said, it came about in the 90s. And even though that's a short term for protoplanetary disk, we now use the term proplid only to describe these kinds of silhouettes of protoplanetary disks. So since the 90s, we've found dozens more. So on the left are 3 images of protoplanetary disks that we found with Hubble. And the thing I want to emphasize about them is that you're actually seeing the surface of the disk in silhouette. Right? Like if I made shadow puppets, right, you would see the shape of my hand on the screen, but you wouldn't see anything about what's going on inside my hand, right? So if you wanted to know how my hand worked, all that would tell you was that it was moving, and this isn't moving on a timescale that we can see. So what's interesting for planet formation is to think about how can we actually observe what's happening inside the protoplanetary disk. So I'm going to pause for a second and tell you that we're going to take a lesson from the TSA. Think about that. All right, everyone knows the answer, right? We're going to go through security. Okay, so the same way that when you go to the airport now and you have to stand in these machines and assume the position, and 2 antennas come rotating around and bounce basically radar off of you, it's happening at millimeter wavelengths. And so these are sensitive to everything above your skin. So it's able to see under your clothes, and it can find the microphone in my pocket. I guess in this case, I put it in my sock, and tell you what's hiding beneath the surface that you couldn't see otherwise. It's exactly the same way with protoplanetary disks. But instead of having to use a radar to bounce a signal off of it and reflect, the disks themselves actually emit in this millimeter radiation. So if we look at a cross-section of this disk, it looks sort of like what you saw in the video, you can see that in the very center are these blobs of dust that are forming planets. And it's very cold in there, right? Because it's shielded by this blanket of gas and dust that's keeping it safe and cold away from the star, because the star is at the center and would be much hotter. So you can see that this cold gas is actually emitting light. It's shining in the millimeter. Further out, where it's warmer, closer to the star, it's shining in the infrared. So these are ways that we can look at the protoplanetary disk. But if we want to see where it's forming, we really have to make these millimeter and submillimeter observations. And I just want to highlight that you see the yellow edge highlighted for scattered light. Towards the end, I'll show you some pictures where we've actually been able to use different wavelengths of light and get it to reflect off the surface of the protoplanetary disk. And you can see the structure that way. So the way we can use millimeter telescopes to see planets uses the fact of radio interferometry. So this means that we will combine lots of telescopes together to simulate a bigger telescope. So I like to think about interferometry like is shown in this image here, which is when you see something in front of you, what's coming to you isn't a fully formed signal of like, oh, this is my computer, right? There are some photons of light that hit your eye does some processing, right? Some cones, and the nerves in your brain sort of process it into then telling me this is a computer. In the same way, radio interferometry uses a lot of telescopes, which are big radio antenna dishes, to take a signal, and then it's got a lot of computers to do what my brain is doing and process that into something that we understand. So you might say, well, why do you need so many antennas? And the answer is that you need a really big antenna to find something so small, like a protoplanetary disk. So if you wanted to see something that showed you about the size of Neptune's orbit, about 30 AU, and you were looking in the millimeter, say 1 millimeter, you would need a telescope that was 1 kilometer in diameter. While humans are pretty good at engineering things, that's kind of hard to build. But if you combine a bunch of smaller telescopes, you can actually simulate that kilometer-sized telescope in the millimeter. And so this is something people have done, and it's not a new technique. So this is an image from a few years ago of a system in that Taurus constellation I showed you, right? Because the Proplids were in Orion, but Taurus is actually closer to us by a factor of 3 or so. And so it's much easier for us to look at protoplanetary disks there because they're closer. And so you can see that here we're not just seeing the surface, we're actually seeing in the midplane. And that's why towards the center it's hotter, right? Because that's where the star would be and heats up the gas. Now I wish to note, the star isn't in this picture because the star doesn't shine in radio. And even if it did, it would just be sort of a small dot in there. But I can see you're not all that impressed, right? You're thinking, all right, she shows us the inside of a protoplanetary disk. It's a blob. I hear you. Astronomers hear you. So, and this is made with Karma, which is about 2 kilometers for its longest length of the antenna. So what did astronomers do? They said, we want more. So Karma isn't shown here, but here you can see a bunch of different observatories. All of the things with the satellite dishes are these interferometry radio arrays. I just want to point out very quickly before we go on, the SMA, which is the second highest one here, which is on a mountaintop in Hawaii. And as someone who studies radio observations of disks at Harvard and the Smithsonian operate the SMA, it means I have work trips to Hawaii. It's a tough life, you know? Okay. But actually, it's really very fun to get to stay up all night and watch the telescope swing all around the sky and make observations of things, not just protoplanetary disks, but everything in astronomy, because the radio universe is a wild and crazy one. But anyway, what I'm going to talk about next is the ALMA Observatory, which you can see they were like, we're going to go higher. So they went higher in a desert in Chile. And the important thing to note here about going higher is that you're trying to reduce the amount of atmosphere that you're going to look through. And that's because the atmosphere has water vapor. And that can actually obscure some of the emission from the disk that we see. So if you think about your microwave and you heat up a mug of water, right, the water gets really hot, but the mug doesn't. And that's because the water is really good at absorbing microwaves. It's exactly like with the atmosphere. And so because of that, we want to minimize the amount of atmosphere between us and the source. So this is what ALMA looks like. You can see the sky is very blue, and that's part of the reason why we go there, right? None of this cloud business that you have tonight here. And I want to show you a video of it because ALMA is really cool. Okay. Oh gosh. Okay. Give me 1 second while we make Alma stop talking to you. Okay, there you go. It's fine. Don't worry. It just wants to tell you how cool it is, and it knows I won't do it justice. Okay. All right, so let's try that again. So Alma is on a plateau, the Chajnantor Plateau in Chile, and you can see it's quite remote from everything. So they have to bring all of this in. And these big trucks, though, are not just used for bringing the telescopes in. They're actually for moving the antennas around the 16-kilometer site. So all of these circles in this drawing are places where you could put the antennas. So you can see them in the far distance in this real image. And you want to move them around on these different bases because you want different configurations to be able to see either a whole wide field image or to zoom in on something, just like when you're adjusting the focus on your camera lens. So when they're moving around, they're not actually taking images, that's just them moving. And even though it's in the radio, we don't take observations in the day so much as in the night because that's when the atmosphere is a little bit stiller. So I know you're all thinking, oh, I just want to learn about ALMA all day. Well, that's great. Well, let's see what it can do. So ALMA, like I said, instead of that 2-kilometer baseline that I showed you for karma, it can get up to about 16 or 15 kilometers. So what can you do with that? I hope you're going to be impressed, right? So this is that same system, HL tau, and you can see that it's not just a blob anymore. So this is something we first saw like this just about a year ago. And the first thing I want you to note, I mean, you could tell this in the blob too, is that it's much bigger than the solar system, right? So an astronomical unit, or an AU, is the distance between the Earth and the Sun. If we take the distance of Neptune from the Sun, about 30 AU, that just fits within that blue circle right there. The green is Uranus. Everything else in our solar system would fit within that dark ring. So everything else is within here. We're somewhere in there. So it's a big monster, right? This is nothing like what we're used to here on Earth. And again, as with the other image, you're not seeing the star directly because it would be very small and it doesn't shine in the radio. But it's hotter towards the center, and that's why it's brighter, this yellow instead of the red. But the thing that gets everyone excited are these gaps that you can see, right? So here you see that I've highlighted some of them, and you can count the number of gaps. It's a lot. And this is something that we had talked about and hoped for as a community, but we hadn't actually had the resolution to be able to see before. So I want to remind you of this movie where we looked at the planets forming, right, and the protoplanetary disk. And this was an old movie from some years ago, right? They didn't know that this is what was going to happen. But they said, well, things are going to move around. They're going to clear out some space. When you look at a protoplanetary disk, maybe that's what you see. And of course, later it all goes away. But if you can get it in that early stage when the star is young and the disk is still there, you should have gaps. There are gaps, okay? And in case you're thinking, well, that's nice that an artist did that, but how do I know that that really is an indication of something, right? It's true that we can't confirm that these are from planets. Planets are one thing that could cause the gaps. But we can go back to that idea of Saturn. So like I mentioned, Saturn's rings host some moons. So here you can see one of the moons and another moon. There's actually a third moon in this picture. If you can find it and show it to me, I'll give you a prize. But I want to focus on this guy right here, right? So this is Prometheus. That's the same planet that I'm showing you the same moon that I'm showing you on the right. And what's really interesting is that Cassini, the spacecraft, can actually watch Prometheus and other moons interacting with the rings, right? So you're going to see it disappear for a second, but you'll see all of that material in the rings getting drawn by Prometheus. It isn't just what's directly in front of him, right? That gravitational influence extends such that you see it moving around. And that's why you've got these wavy patterns in the ring of this bigger image, right? Because Prometheus is affecting his rings. It's exactly the same way in a protoplanetary disk, that a little planet can cause these changes in its ring. And one thing you'll note here is that we had to actually send a spacecraft to Saturn to see this, right? We couldn't see this here on Earth because it's such a small thing making a change on such a large scale. So the chances that in a protoplanetary disk that we're going to be able to see a planet in action are very small. So instead, the best thing we can look for are these gaps. So that's basically the highlight of the talk, but now we'll try some other things, right? Because it's fine to say that gaps might be caused by planets, but maybe you don't believe me. That's fine. But one thing that might also be an indication of planets are these scattered light images. So this is not the midplane. This is that light bouncing off the disk. But it's shown us for these two and one more system that some of these protoplanetary disks look kind of like galaxies. They've got these spiral arms coming around. In the middle, the light from the star has been blocked. That's why you see a black circle. So the reason I say that these could be indications of planets is because of some modeling work we've done to think about planet formation. So planet formation, like many fields in astronomy, goes down two paths, the observations and the theory route. And the theory route involves lots of modeling and computer simulations. So using one of these computer simulations, people said, I wonder if I could match that picture on the left. And they said, I think I can. And so what they found is that by adding a planet into the system, and not just some perturbation from some theory that we had before, that by putting a planet up where you see that X, that could explain those spiral arms. And it's very hard to get spiral arms in other ways without having a planet there. So is that definitely a planet? Are gaps definitely caused by planets? I don't know. Probably it's not sure, but we do know it could be caused by a planet. So these are all indications of planets forming, but you came for the big things. You wanted to see if we could see planets forming. If we had had this conversation last spring, the answer would have been no. But luckily, time has passed. So on the left, you see, again, this is in the millimeter. So this is actually, I believe, taken with the SMA. You can see an image of lit calcium-15, and you notice that this ring, this disk, unlike the others, has a hole in it, right? There's this dark spot. It's not that we've blocked that out. That's actually what it looks like when you take its picture. And the funny thing is, when you look at it, actually in infrared light, and also in the visible, you see things there. So what you can see, and I've zoomed it up so that you can see, are a couple planets. Okay, that's cool. But what's actually most exciting is that we're seeing planet formation in action. Because you see the red spots, B and C, and C also has some green. Let's forget about D for now. But the thing that's really exciting is the blue stuff on B. That blue stuff is gas at 10,000 degrees Kelvin, and it's actually falling onto that planet. So this is an idea, an indication of a planet actually accreting. It's growing and it's collecting gas. And so this is explaining why, maybe there's a hole in that disk because the star is clearing out some of the material, but also planets moving around are clearing it out. And we can actually see the stars themselves forming planets. So this is just an awe-inspiring picture. And together with that information about gaps being seen in disks or spirals, we now can say that we know something about where do planets come from, right? We can't explain the whole story with observations. We need a lot of theory in between that we can try and test against our models. But we do know something about where do planets come from, right? We know that they come from protoplanetary disks that are centered around stars, and that they're made out of this dust and gas and ice that has to grow just by immense amounts, from micron sizes to thousands and thousands of kilometers, to be the planets that we know of today. And so we're doing this, right, by not just using our old techniques of looking at the solar system, but by also looking for protoplanetary disks far and wide. And as we do this, we can complement this with research on meteorites to actually look at the materials that we're finding. So as we're going forward, you might say, well, now what? Like, you found a planet. Great. Well, we're going to keep doing this and to see what else we can find. Just like when we discovered the first exoplanet, that was really exciting. But then everyone said, well, where's Earth, right? Well, we're just going to keep going, and not just to find Earth, but a lot more. And as we do so, the best way that we can study this, right, is actually by studying these protoplanetary disks. There's no other way that we can study planet formation. So with that, I'll end there. And I just want to remind all of you, especially in the overflow rooms, to come and see the meteorites in the auditorium afterwards. And don't touch them, otherwise you might end up like the dinosaurs. Okay? With that, I'll stop. Thank you.
Questions and answers, and we already have a question right over there, sir.
Well, you mentioned something about using radioactive isotopes to date things that were in those meteorites. Mm-hmm. And I think I understand a little bit about how people get a baseline for the isotope ratios on Earth, but what sets the starting time for something like that?
So so the question is, how do we date the meteorite, basically? What are we comparing it to? And the answer comes to us based on the idea that the protoplanetary disk forms out of the same material that the star forms out of, the sun. So we can study the sun and its composition very precisely, looking at the light that's shining off of that. right? We can do spectroscopy, we can break the light up into all different wavelengths and see what we find there. So given what we know about the sun, we can then compare that to meteorites, and we can look at, for example, the amount of lead or uranium decaying and get a sense of the meteorite. And when I say it's older than the Earth, you might ask, well, where on Earth are you comparing it to, right? If you compare it to my backyard, that might not be that old. And the answer is they compare it to rocks in the deep sea floor, not by the continental crust, but further out. That is actually sort of the oldest rocks on Earth. So I hope that starts to give you an idea of how this process works. Other questions?
There's a young gentleman up in the balcony.
All right.
Have you found a moon that has a moon?
Have we found a moon that has a moon? Right, so right now the answer is no. But the idea of how a moon might have a moon is actually really interesting, because the way that you get moons and rings around planets is the same way that you get, a protoplanetary disk around a star. It all forms out of the same kind of thing. I think, though, we wouldn't call a moon around a moon a moon. I think we'd call the thing going around it maybe more of just another satellite, so it could be an asteroid or something else that it's captured in its orbit. Good question.
Interesting question.
All right, over there.
Are there any better explanations on why, I know you didn't talk about this, but it isn't something that's on my mind, on why Uranus and Venus, why their orbits are different?
So one thing that I didn't talk about is, what do planet formation theories say about all orbits always, right? I said that within the solar system we're all going around the sun in the same direction, so you might think planets always have to go around their star in the same direction. When we looked at exoplanets, one thing we found pretty quickly was that you're not always going around in the same direction. And a lot of what's happening after you formed your planet, or even along the way, is that things are jostling you around, so you can easily, or not, change your orbital configuration. So what's causing that, it's not a certain answer, but it's just some issues of migration, and that, like I said, affects a lot of planets outside of our solar system. So we're still not sure, and that's why we don't talk about it that much. Other questions in the back?
I have a silly question.
Yeah.
So if planets are created with the planetary disk around the creation of a star, why don't all stars have planets?
So,
Repeat that one. I didn't quite
so
hear
the
it.
question was, if planets form in disks around stars, why don't all stars have planets? And the answer is, most stars, we think, or almost all of them, do have planets, right? By finding, right, I see her going like this, right? I mean, that's the thing, right? That was like the starting point of this talk, and it took us, right, millennia to get to that realization. But now we think, so when you look out at the stars at night, you can say, there's a planet around that. You're not going to be able to see it, but you can certainly believe it. And so when I say not all stars, right, some stars are different. Some want to be a black hole or something, right? Although even some of these more exotic things do have planets, like pulsars, which are which are stars that are old and very dense. So they're neutron stars, and they're spinning really rapidly. And that's actually, around these pulsars was how the first exoplanets were discovered. So all kinds of stars have planets, and so we do think they're all out there. All right, yes?
A lot of the planets in our solar system have iron cores. Is that because they're stronger, so when they collide, they don't have, like, they don't break apart because it's a stronger material, or is there another reason why?
Okay, so the question is, a lot of the cores of the planets in the solar system are made of iron. So this is an iron meteorite. It's very heavy, as I mentioned. It's got a cool pattern. But the thing about the meteorites, right, that are mainly iron versus rocky, is that iron is one of these things that's produced very abundantly by stars, right? So all of the material in our solar system comes from other stars that have ended their lifetime, right? There are things that are heavier than iron, that are sort of stronger, so to speak, but they're not as abundant as iron. So if you're going to collect enough of it, right, it's going to be the thing that's around the most, not necessarily the strongest. Other questions? Yeah.
So I have a question about the planetary nebula. When it leaves the core of the star and it starts to float away, is there a possibility for reconcentration of that material to form other things like planets or?
So just to clarify, when you say it floats away, what do you mean?
Like, as far as I understand it, it starts when the star begins to die, it expands until it forms this cloud that leaves behind the white dwarf in the center of it. So I'm wondering if it's possible for that cloud to reconcentrate into another object.
So there are a couple of things there, right? So asking about what happens when a star dies and all of that material from the star sort of goes outwards. And how does that affect planet formation? So one thing I do want to clarify is everything I was talking about a protoplanetary disk pertains to when the star is very young. So when we're seeing these systems, they're around young stars. They're much younger than the Earth. Because when they're late in life, you have something left over that's called a debris disk. So if you see the Kuiper belt, right, where Pluto hangs out, that's part of our debris disk. And that's left over from planet formation and also from planetesimals bashing into each other and creating more dust, which you can see as the zodiacal light. So planet formation is mainly happening when the star is young. And a lot of that is because you need a lot of gas to form planets. Because like you saw in that movie, the gas is sort of driving the planetesimals towards each other. If it's dry, the planetesimals aren't going to, suddenly get up and move into another one. And as a star ages, like when the sun expands in other stars, it can actually envelop the planets that are there. But again, you don't have the concentrations in the right amount of materials to then start forming new planets, is my understanding. Up there, we've got...
Why do meteors crash on Earth?
So the question is, why do meteors crash on Earth? So the way you asked that question, you actually answered your own question. Because when it's in space, we call it an asteroid. When it enters our atmosphere, we call it a meteor. When it lands on the ground, we call it a meteorite. So we just happen to call the things that enter our atmosphere meteors. But why do they crash into us instead of staying away? Why don't we have a force field? Well, that's just because some things are on different orbits and happen to get through us, but we actually do have a pretty strong atmosphere that burns up a lot of stuff before it comes all the way to the ground. So that's why we're safe most of the time. But if you look at the moon is just full of craters, right? And that's because it doesn't have an awesome atmosphere like we do. All right, in the front.
You might have explained it. I don't remember why does it form on a plane like the way it does?
Okay, so the question is, why is the protoplanetary disk a disk and not something else? So if I knew how to make pizza better, we could do a demonstration. But the idea is that things start as a cloud, which is sort of like a big sphere, and that's a very stable gravitational configuration. But as things are in your cloud, they're not just staying still. They all have these random motions. And from the random motions in total, there's going to be sort of a preferred direction, shall we say. Like if you add all of them up, there's going to be sort of some direction of rotation that more of them are going in or not. So that means your cloud is going to be spinning a little bit. So as your cloud is spinning, the gravity is still holding it, and it can still collapse towards the center. But when it's spinning, things are pushing outwards. That's that force that you learned about in school. You might have called it centrifugal, whatever. As a physicist, we're not going to have my issues with that. Anyway, spinning things have an outward force, right? So once your cloud is collapsing, it can collapse up and down. But in that plane, it can't collapse inwards, right? It can't collapse to a point. So that's why things settle to a disk, because up and down come down, but spinning stays out.
Let's do two more really good questions.
Oh, the stress. All right, one over here.
Why does water make it easier for dust particles to stick to it?
So the question is, why does water make it easier for dust to stick to particles? So I think you're referring to, in the talk I said ice makes it easier for dust to grow. So it isn't necessarily water, right? Ice can be anything cold. So carbon monoxide, when it's frozen, can be ice. And I don't think there's a good theoretical reason for it. I think this is just something we find by experimenting in the lab with different grains of stuff to see what sticks better. And you, sir?
When I was a boy, it wasn't known why the asteroid belt was there. Is that understood now by astrophysicists?
So the question is, why is the asteroid belt there? Do we know the answer? Right. So again, the asteroid belt is sort of between Mars and Jupiter, and is where all of these lovely objects come to us from. And I think the understanding is it's part of the protoplanetary disk, and from this nebular hypothesis, which was really favored starting in the late 70s. So I'm not sure if that the time scales. You look like quite a young man, so maybe not. But I hope that answers your question.
Why didn't it form a planet?
So Right, so like I was mentioning before, why didn't this all form a planet, right? You need a lot of things going on to form a planet. So when you have this debris in the asteroid belt, not all of it is large enough or sticky enough to grow, but also, again, you need a lot of gas to form a planet. So the gas is going to dissipate over time, right? Just like air goes out of your balloon over time. So also part of it is just timing. So even if you have all that material there, it doesn't necessarily form into a planet if the gas is gone.
Did the gravity of the other planets also affect things?
So Jupiter helped direct things to where they are now between Mars and Jupiter. But in terms of why it didn't form another planet, I don't think that has too much to do with it. But I'm not sure.
Okay. All right. I asked because I was wondering too. And with that, we are going to close out our program. So thank you all for joining us, and I hope that you'll return next month. And thank you.